Okay, let's get to the last part of today's lecture. First, we are talking about how to process chip-seq data. The first, we'd like to see how to evaluate fragment data. How to determine the length of a fragment. And the first question is why there is a size distribution, and why? Because size detected in the sample stage is sharing, and then we have a PCR step which favors shorter fragment, and size of fragments are usually determined can be determined by the computational approaches. The size distribution also will be used for peak detection. Then you may confuse why we need this one to determine the peak. And I first introduced like a tag shift or tag extension can be used to detect the peak. Then let's say why we need that. And as I said, when we do sequencing, and we have a both strain and the positive strain and the negative strain, and which is a strain dependent by modulating. And here I show you an example. This is a protein binding, transcription factor binding here. When you do sharing and you get the sequence from this part, no problem, but you cannot get this one because it's protected. And you also can get it from this side. Then when you map into the all sequence in this region, you may get a peak on the positive strain like this way, and also you get a false. You get another strain in the negative strain. You get another distribution in the negative strain. So this means upstream or downstream, and you can see they have a separate distance. And those two peaks, they are not both in the. They are not in the middle. That's the reason why we need to know the technology or protocol for this of chip-seq. From technology, you already know, of course, because this part has been protected, so you cannot detect this side. Then the first thing you have to know how much the distance here. Then you may guess this binding side is in the middle of that one. One thing we can do is we use a cross correlation of positive and negative strain. So when we do that, we can get a peak. Do you have idea cross correlation? Okay, then maybe you can get a peak here. So which means this peak represents the chip peak and this represents the effective fragment size. But you also can, for random sequence, you can get something here. But that's not the peak because there's small, in the correlation, we can see a small peak. That's not the binding side. That's only for the sequence read length. So they show peak here, which we call the phantom peak. So these two are very different. And from the true signal one, you can see the high peak shows somewhere here, not the phantom peak. However, if you have some sample, and after sequencing, after analyze, you get this pattern. This is still the red is one sample, and the blue is another sample. Green is a control or random one, and how you can interpret this data for the cross validation. We still observe the one here, which may represent the effective fragment size. But we observe the very strong signal and the phantom peak here, which means this sample may not quite good. There is a poorly enriched or very few binding sites enriched here. Most are random here. So based on cross correlation, you also can find the quality issue of that one. Of course, and we have several patterns. I don't need to talk about this one here. Now, the second process is we know the effective fragment size. We want to know and I know you have been waited for 2 hours. You want to know how we detect the peak. For the peak detection can be used for chip-seq, DNA-seq, or tag-seq. The overall of this peak detection, of course, we want to identify the region with chip-enriched fragments, which is basically enrichment analysis, but based on the read density. As I said, okay, let's say example we showed before. If we found that there is a peak here, a number of sequences identified in this region compared to very few or even none in the control, then we may say, okay, this is a peak. And there is a number, there are many tools can be used to identify peak. For example, MAX is the most popular one now, and the CSER, which used to identify broad chip-enriched region. You may ask me a question, why we call it broad here? I will explain later. And also hotspot, which was used by ENCODE project, and a number of others like FSeq, Zimbab, PICSeq, EPIC, and all of them pretty similar. Theoretically, they are very similar, but they have some detailed difference in the algorithm. And we have to consider when we call peak, one thing is enrichment. The other one, as I emphasized several times, is control samples. Then you know how to compare. For the most chip-seq data, and like a transcription factor, as we showed before, NISF, CDCF, ST1, the binding site is a kind of significant. Don't be surprised to see peak here. That's what I said. From the positive strand, the negative strand, you may see separate peak here. But when you simply total put them together, forget about the strand put together, and in the middle you also see they have not much sequence here because the sequence cannot be is protected by the protein binding layer, and then. But still, we call this, if it's not broad, we call this a punctuated enrichment, or another way, we call this peak as a narrow peak. However, for other things, it's not, we call it non-point fashion, especially for most of histone marks and also other chromatin domain signatures. And the peak, hard to say peak where they are, right? Or maybe you can say, okay, this is a peak, this is a peak. They are peak or not. It's hard to say. But actually, for some histone modification, and like this one, H3K27 trimethylation, you can see there is a broad peak here, which we call the broad peak because it's a diffused, the signal diffused or very diverse. And also, there is another one. For example, here I tested Poly2, which is an important machine for transcription factor for transcription, and which is a mixture of punctuated and broad signal. And you can see at the transcription start side, the Poly2 layer is a narrow peak, but downstream of transcription start side somewhere, they also show somewhere here. That's because the machinery of itself is just go around. It's like machine move around and let the sequence transcript. So it's not surprising. So that's what I said. Which peak we need to call totally depends on what you are going to study here. So peak finders are only for the first scenario and identify binding site of a protein of very specific sequence preference. So what we do, and we can do a number of steps, like we try to signal profile around enrichment chromosome, identify potential signal region, then we compare, we use a background noise control to build a background model, and then compare with that one. And we also have to remove artificial peaks. And in ENCODE website or somewhere, I believe they have a backlist. They put some genome artificial peaks for whatever they put there, and you can compare with that one, remove the peak you caught. And also they rank all significant caught peaks, and there is shows here 1,000 dozens of algorithms are available for this topic. I don't think we need to revisit the ChIP-seq protocol because you cannot wait anymore. But at least I show some picture here. It's again, and it's a positive strain, negative strain. We have two peaks, but how we identify? Can we simply say, okay, we call this one, and then we say, okay, we have a middle site? You can, but it's not good. Or maybe you can say, can I merge this one, just reverse that negative strain and merge that one? Then you have to be careful. If they are very close to each other, when you reverse that one, oh, beautiful, you see the peak in the middle. Or even it's not far away, you see somewhere here. But if it's far away, you may not see a peak here. Then what can you do? So this reminds us we have to shift both strand peaks from 5' to 3' forward 3' to somewhere, and meet the half of fragment size. Then you may understand why we need to evaluate fragment size. Because the fragment size will determine how much we will shift the loss sequence. Or maybe some people, they use the extension somewhere, the extension mean fragment length to somewhere, then they call the peak and they'll try to identify that one. The advantage of tag extension before signal detection, because for the tag fragments size detection, we need to do signal detection. But for the tag extension, they may not need that one. They just evaluate the fragment length and then they extend it to somewhere. They can correct some assumed fragment length and also smooth over gaps that were not tagged, just because of the low sampling or rhythm probability issue. Like for this one, if we also can use a window to slide somewhere. So each window, they have for the sequence without window, we have a sequence information for each single nucleotide. But with window, for example, we can use a 10 nucleotide window, and then we can sum over the sequence within the window, and we can get a smooth signal. And the smooth signal, maybe they can denoise, and also they can fit broader statistics tools like Poisson or negative binomial. And some algorithm, they use this one. Here is one example shows before, that's a raw signal, original signal of one, which the data is got from Dr. Kun Huang when he was in USA or OSU. Now he's in our IU campus now. And the original histogram, you can see a bunch of signal here. But after window size remove, and then you can see quite smooth. And some area, even no signal, but after smooth, we can see some signal here. So it become flat. Then we may know this is this is party 2. Then we know, okay, from this one, we know peak here, we know sharp peak here, but it's hard to determine what are they here. But after smooth, we can say, okay, there is a broad peak followed by following the sharp peak here along the transcription start side. As I said, okay, we need the model for the background or for the control. So the reason we need that is for that tag total, we can build a statistical significance of the tag clustering depends on the expected background pattern. And some assumption is a background tag density is distributed uniformly around the genome and independent between strands, even though we know it's not true, but it's an assumption we can use. So for that one, the sources of non-binding enrichment it could be variation of chromatin accessibility, as I introduced at the very beginning, and also sequencing related variation mapability, sequence compensation. They can choose that, but still we can get the kind of universe one, but in some specific area, no, not really. So for that universe one, we use a true signal, compare that one, we can get a p-value, and then we can get the enrichment ratio and related to the background. That's the two criteria we need to identify or call the peak. To call a peak, we need as I said, we need a constructor background. And if we know control, we definitely need that one. With negative control or compare two conditions, we also need that one to do that. And this is kind of redundant from previous one. I said we need no control or some control. Forget about that. And now we need a core peak. What are the peak? So main quality criterion is either an absolute signal threshold or a minimum enrichment relative to the background, or both. I prefer both. So in other words, we need a significant, we also need the enrichment signal is strong, but we also want to know absolute value, how strong the signal of this peak is. We also need that one. But in most cases, people only care about the enrichment signal. And different softwares can be used as like a blah blah somewhere, and the p-value from different but just to remind you, the p-values from different methods or models, they are not compatible. Don't compare like okay, this peak I called max is a very significant, but from another one is not quite significant. This max is 10 to minus 9, but from other like Caesar or whatever you use, there is a 10 to minus 8. Why is significant? Why is a little bit less significant? No, don't compare with the different methods. And also, we want to do post detection field. One thing is we, as I mentioned, we know tag directionally, fraction of a number and the positive and the negative tags. We want to know they both show there. If they show only one, either one line, maybe they are not quite good. So shows here, we have to eliminate the tags of single side that shows count much greater than expected by chance. By one chance, that's not good. Just forget about that one. And then this is a transcription factor binding or some histone modification. But for general, like computation, what's the computation method to identify chromatin signatures? We know for heterochromatin, which we assign the downstream gene, and for urochromatin, they may active or silent. For either way, also depends on many factors like transcription factor, whether transcription factor binding here, or is there activations signaling for histone modification. Many histone marks could determine that one too. And for the non-point, usually it shows a non-point fashion as I showed, and it's a very broad peak scale. So histone marks and other promoting domain signals, they have such a signature. And they could, the range could from nucleus some size, so it's about 150 base pair domain to very broadly enriched region. So another popular one and the method which called a Caesar, they use it to identify cheap enriched region for broad region. I don't want to go through this one, just to give you the main idea. The first thing they have a preset window. So for each window, they have a signal like this one. Then they compare the either control or negative or background. They want to see if this window is a significant or not. For significant window, they cluster them together. And then even you have some gaps between different clusters, between neighboring clusters, they have a cutoff here. If they allow only one gap here, then they can merge that one to a broad peak, which is kind of powerful in that, for example, of course, the peak, for example, here shows H3K27 trimethylation. And we have a peak, if we allow only, we use window size, of course, here we want to show how window size and allow the gap, we are change the final calling peak. For this one, from your intuition, you may say, okay, I found this is a peak. definitely. Forget about the control or negative or background here. We assume they are uniformly distributed. And there is a peak here. There is a peak here, or maybe here. So maybe you can say there is a 1, 2, 3, 4, 5, or even more for this one. But when you use this one, totally depends on the window size you use. For example, if you use window size you may not see clearly, it's a 50. Maybe you call 1, 2, 3, 4, 5, 6, or up to about 10. But if you use a wider window size, like 100, double window size, you may get this is one peak. This is one peak, and that's another one peak. Or even you use more, like 200, you only get 2. Or even you use, of course, if much wider, you may get, okay, those are only one peak. So let's maybe answer another question. And the gentleman asked me when we will break, and he asked me how many peaks, the number, do we have a formula to calculate how many peaks, the number of peaks? I said no. It totally depends on the algorithm, totally depends on the parameters you used. And of course, it also depends on, by this method, Caesar, it also depends on the gap you allowed. For example, if you use even we focus on this window size 200. If you allow one, no, you don't allow the gap. Even the same window size, you get this one is a 1, 2, because there is a small gap here and something here. But if you allow 1 or 2 or even 3, okay, you can find they merged together. So also depends on both one. So it's hard to say which way is good. But in general, unless you have a biological sense, again, I have to emphasize biological knowledge. If you have that sense, okay, from ENCODE and other algorithm, maybe hotspot here, they call this is a peak, this is a peak, and there's a number of peaks here, number of peaks here. It's kind of an individual one. It's more like a narrow peak. But if you say, okay, that's not what I want, because I know this histone modification, they have a very diverse or broad peak. So maybe you can use this one to call a peak here. You must want to know, okay, that's this paper published in PLOS One, I forgot which year, and they use a different algorithm use a different peak cause algorithm to identify open chromatin region for the DNAS sequence for use this one. They use the 4 algorithms, which is a hotspot and was popular by ENCODE project and the FSeq and the MAX and the Zimba, and they say they identify in different cell lines, and they want to see how they look like. You can see, we cannot see majority can be identified by all of them. It's not so many, but still, and we see some overlap, some level overlap between different algorithms. So it's hard to say which one is good or which one is not. So then you make, as I said, you may become frustrated. Then what can I do, right? What can I do? One thing you can do is talk to the biologists. They did a sequence, ask them what they have done. Another one is check with the profile, like this one, and to see what you can observe, and to try to find the best parameter you can use to copy. That's what my experience. And now, next one, I want to introduce another most popular algorithm to copy is called MAX. MAX, the full name MAX is a model-based analysis of ChIP-seq. It's originally came from the ChIP-seq analysis, but now can be used a very broad sequence analysis like histone modification or something. The MAX they used, as I said, first we know and there is a positive strand tax and the negative strand tax. And the first MAX they have some algorithm to evaluate, estimate the region of DNA to estimate the shift. They use a shift model to estimate the fragment size. They determine what's the effective shift size we can use is best for the model. And then with this parameter, Max2 links the nearby highly enriched regions. That's the Max2 they used. For the first version of Max, they called Max 1.4 or whatever, and they only identified the nanopeak. And in the next version, next generation version, they link the nearby highly enriched regions, which is pretty similar to CSER. And the maximum linked region is 4 times of the fragment length. They use the fragment length 4 times. And this enables Max2 to find a large region, pretty similar to CSER or other algorithm to use that to identify broader regions. The general step of Max is the reason I want to discuss the more details about Max is I want you in next week you have a hand-on practice on Max because this one is the most popular one we use. And first they estimate the fragment size and make a corresponding adjustment for read position. And based on the model of Poisson distribution, they can for the background signal they can determine the candidate peaks with a p-value smaller than cutoff. And then they identify local noise to estimate the parameter lambda by using different size of windows from 1,000, 2,000, 5,000 to 10,000 around the candidate peaks to use the maximum lambda as the local parameter. Then they calculate the p-value with respect to this above local regions for each candidate peak, then remove those false positive ones. This is promising. And then another thing is that they can determine the summit position, which has a maximum density within detected enriched region. Of course, the summit position is not in the middle of the peak. It's maybe shifted to 3' or to the 5'. But we can use the maximum density to determine the summit position. And another thing I have to emphasize here, why summit position is important. You say, okay, I already got the peak. Why don't I care about the summit position? Summit position, when you study transcription factor, especially when you want to know exact transcription factor binding site or you want to identify some novel binding site, this summit position is very important. It can be narrowed down your search area to very narrow region. And they can estimate the false discovery rate by swapping treatment and control, call some peaks, and then they say how many false peaks can be called, and they have a formula to define false discovery rate. And this can remind us how many false discovery rate we get based on this parameter. And the whole menu or comments of Max2 you can find it from this website. Briefly, in general, they have 2 pipeline to call peak. One is for nanopeak, and they use Max2 and they call peak, and the -T means foreground or treatment. This is the signal, true signal, and this is a signal you already got, the sequence signal. This is control here. If you don't have, unfortunately, if you don't have control, you may ignore this part. And this is the format that shows is a BAM or is something else. This is a genome, which shows is a human. This is a -N, shows the test, and also this is -B, that is the cutoff of that one. Even I have to go back to check which one is which and what's that mean. And for the broad peak, you can see the difference is that they use a specific cutoff they call the broad cutoff, which is different from the Q cutoff. Q value used in nanopeak. And also they have emphasized this is a broad peak. For this one is a default is a nanopeak. And sounds like very simple, right? And if you think it's a very simple, I have to say that's because you are too young, too simple, or sometimes naive. Yeah, that's a Chinese story. If you don't understand it, you may ask your Chinese classmate, what's that mean? And to be honest, and this one is, I won't say it's complicated, but it's very detailed. That's the reason why we like that. Even for different platform, different studies, you always can find the most appropriate model you can use for your study. So they have when you go to the website, you can find that there is a number of comments there. I don't expect that you can know exactly everyone before the end of the class. No, but the next week, Sean will show you several examples to see how different if you use the wrong calling pick or wrong comments, maybe you can get some trouble. So that we just want to remind you, and maybe in the homework you can do some things. Of course, in the final exam, we may ask some question about that one. So focus on Max 2, but you just understand the other algorithm. Main part is fine, but the Max 2, I hope you can grab most of this part to see what's going on. As I said, as I showed many times, we have a different peaks, different type of peaks, narrow peak, broad peak, and gapped peaks. And for different ones, you may choose a different algorithm. You may choose a different parameter or algorithms. And then another thing I want to show you is Max2 output, the format. The format output is pretty good, except the final one. I still don't understand why they have this one. It is occupies so many spaces. I hate that one. But for the first one, they shows the peak chromosome location from start side, end side, and the length, and the absolute summit pipe ups, like corresponding to the signal here. And also the p-value, but in the negative log 10, and the photo enrichment compared to the background or noise, and the Q value. So basically, we use these two. If you want to use, we use these two to determine which one is. We determine the true peak we need calling. This two is important, but the Max 2 in Max 1.4 or the early version, they have some summit position, which is very good. I think they missed the summit position in the Max 2 output. Shane, do you remember, do they have a summit position in the Max 2 output or no? They do? Okay. Maybe you can find that, ask Shane. Yeah. And now let's go back very early. Do we need the chips? Do we need a replicates or not? If we have of course, if we have two replicates and we find that we call it the same peak, same area, we are happy. We have high confidence and say that one. But if we found the peak called from one sample, but not in another sample, the other sample, then will you be sad? Or you said, okay, that could be false positive. I don't suggest you do that. It may be, but maybe not. I will say that in the final slides. And the people developed the algorithm they call the producible discovery rate. Try to see how similar those are. Like, for example, they have one sample here and one replicate here, the other replicate here, and they see correlation here. They call this portion as a identify one, but you just understand that they try to see the correlation between two samples. That's all. And about the quality, we emphasized many times quality, but we don't have a parameter. So far, we have not shown any parameter to identify the quality. In the ENCODE, they have a very good quality metrics. They have a number of metrics to test whether this one is good or not. And I copy paste most of the part here, so you can go through one by one. And if you don't like my slides, you can go to the website to check one by one. I won't wasted too much time here because I know you can't wait to go home. But finally, I want to show you something about, as I promised, show you from based on our bioinformatics side, how we can say the quality is good or bad. We have one example here. This is a paper published on somewhere, and they show they do EGR1, which is a transcription factor, the binding site. They use a ChIP-seq to identify binding site in the K562 cell lines. And as I showed you before, they found this one, there is a higher phantom peak here. Of course, they have some peak here. We may, based on this one, we already have a rough idea. Maybe the sampling pool is not good, or some issue happened, right? And or some bias. But still, we need more evidence. You cannot show them here. Say, okay, it's not good. Go back. They will not be happy to see that. So we checked. We use another parameter. I didn't show here. Yeah, I showed in previous slide, but I just skipped that one. It's we call it FRIP. FRIP means the reads. We get this data. We assume they are good. Then we call peaks. Then we see within the week how many sequences locating within the week. The ratio is pretty low here. So and then we see, okay, how many regions we can count here. You can see only few thousand count here, and even the replicate one, even only few hundreds here. Then we have two more parameters to support our conclusion. These two samples could be pooling. Then we can talk to biologists and say sorry, and this quality may not good. You'd better to redo that. Then they redo that. You can see after the second round, and you can see this fragment size, we show strong signal here. Of course, we still see some weird signal, quite weird signal here. But this one is good enough, especially when we look at the peak and how many sequences located at the peak. We use the same cutoff. Sorry, not we. They use the same cutoff. They found the ratio is much higher than first round. And especially number of regions they can get is much higher than that. I believe they are much happy. They were very happy about the second round of that one. That's what we need to examine that one, to how to show the biologist is good or not good, and how many you can get, and do you need an improvement or something like that. That's the important part for the data interpretation. Okay, and then another thing, we talked many about the footprint computation method, and we want to show you and the number of, just keep in mind, and for the THS sequence and the ATAC sequence, and we have an advantage, take advantage of that technology. We can identify transcription factor binding too, but the problem is how can you identify the whole region? I mean, like the sharp whole region. That's the challenge of that one. There is a review paper still. There is no best algorithm to call that one, but there is a few popular one. King, DNS2TF, and the PIQ, and we prefer DNS2TF is a kind of good. And this one, I want to ask you to get as much as, I mean, like I want to ask you to be an expert of footprint coding, and to, sorry, I need to take a second break. But I want you to understand how many algorithms can use to that. What's the type of that one? I leave that as your homework to understand what are they and how many are there. And as I told you, you can remember in mind that when next time when you go find work for interview, people ask you what you used to call footprint, and you may say, okay, I think DNS2TF is good. Then people say, oh, you are quite good, right? It's good for you. And the important thing is that as I said, we need to find a cleavage pattern. And people use a different algorithm, either called a segmentation-based or use a site-centered method, and they try to identify the transcription factor binding site. But just remember, what they do is that they use already known canonical motifs from the database, either from whatever database like Mimi or somewhere. They use that one. They scan the transcription factor, try to find which sequence matched already know one. Then they identify, okay, probably this transcription factor binding here. But this technology, the reason I don't want to talk much about this technology because I don't want to mislead you guys. Technology is promising, but still they have many challenges. I will show you in next slide. And then this one, how to do that? That's the next lecture contents we need to talk about. How we can do motif-based predictions, or how can we use position-weighted matrix to scan the sequence to try to find the best match side or predict the binding side. That's the next lecture we need to talk about. Okay, I promise this is the last slide of today. We have many biological challenges. One thing is, as I mentioned several times, all the process is dynamic biologically. Kinetics is a challenge which none of this method can adjust, has adjusted completely. Even for example, replicates, as I said, replicates, definitely we have replicates. If we get consistent, we are happy to say that. But if it's not consistent, if the rate is lower, what we can say? Can we say, okay, too bad, I have to go back to do another one? You can try, but probably, also there is a probably. As I said, transcription factor, whatever the technology, it's a screenshot, its own time. And you know it's a dynamic. Maybe you catch it this time, next time you get a different one. So I only expect so many overlap between two replicates, okay, for most study, not for all study. And also another thing is about the footprint. Why I said the footprint also has challenge? Still, same thing. Because many dynamic transcription factors, for example, is a GR or external ER or some serum response factor or transcription factor involved in cell growth and differentiation, they bind the DAA. We need the sitting there. Then when we do sequence pull down, because they protect those sequences, we cannot, when we have an adapter, for example, ATAC signal, we have an adapter insert there. They need to sit there to block those sides. Then we can see a big hole, then we can identify. But the question is, if they are not happy to sit there, they want to go around, what we can do? Probably you cannot see any footprint. But don't be sad, again, this might be the true biological. It doesn't mean you failed or it doesn't mean something was wrong, but which means a biological challenge there, okay? The reason I want to mention that is in future, when you get a number of ATAC signal, you identify big, but when you want to see cleavage hole there, and you said, okay, not everyone has that one, some of, or maybe 50% of, they cannot show that, so what I can do? Maybe some, not 50% of some percent, but I say, okay, let's choose, that's biological process. So as bioinformaticians, definitely we need to understand the algorithm mathematically, and we know which software, we know which algorithm, we know which pipeline is the best for that one. But in the meantime, even after we get the data, we call the pigs here, we have to correctly interpret the data, interpret them. Not just say, okay, I got those there, and you have to find one by one, and all are there. No, that's not a way. So that's the reason why bioinformaticians have to study biology. Me too. Yeah, I'm still studying many biologists. Yeah. Okay, hope you guys enjoy the lecture, and we'll see you next week. Yeah.